We now move on to considering a particle in a box. This is a way of considering a particle, for example an electron, which might be constrained within an atom. It isn't precisely right, but it gives a general idea. So here is the box. It is a box such that the potential outside the box has a value V0, but the potential inside the box is 0. The length of the box is L. So if a particle is inside the box, it can't get out unless it has energy to overcome the potential barrier of V0. The Schrodinger equation is minus h bar squared over 2m d2 psi by dx squared plus v psi equals e psi. And we can write that as minus h bar squared over 2m d2 psi dx squared equals e minus v all times psi. And if we multiply through by minus 2m over h bar squared, we get that d2 psi over dx squared equals 2m over h bar squared, and then for the minus we just simply reverse this and it becomes v minus e times psi. Now I am going to call this term k squared. So d2 psi by dx squared equals k squared psi, where k squared is 2m over h bar squared v minus e. Now that is satisfied by the formula that psi equals ae to the kx plus be to the minus kx. You don't need any I terms here because we haven't got a minus term to worry about. I can prove that that's the case. d2 psi by dx squared, you simply bring down k twice, that becomes k squared, minus k twice becomes minus k all squared, which is of course k squared. So that is simply k squared times the original function, which is psi. Now, the first thing we can notice is that that term must disappear. Why? Because e to the kx is an exponential term that just increases exponentially. And that means that as x increases, the wave function increases to infinity. And that can't be right. So we delete that term and we are simply left with a wave function that is psi equals be to the minus kx. And I remind you that k squared is 2m over h bar squared v minus e. And this is outside the box because we're talking about a potential here. So what is actually happening outside the box? Well, outside the box, this is the box here, but outside the box, the potential, the wave function is falling exponentially. And the greater v is, that is, the greater the size of the potential, or if you like, the deeper the box, the faster this exponential term will fall off, until eventually, when v is infinity, in other words, the box is infinitely deep, the exponential term effectively falls to 0 immediately. But what does that actually tell us about this box? Well, it says, there's the box, it says that outside the box, if the box is not infinitely deep, the wave function falls off. Which means that at, for example, this point here, the wave function may be small, but it is finite. And if psi is small but finite, then psi squared is small and finite. But psi squared represents the probability of finding the particle at that point. And so what this tells us is that there's a small but finite probability of finding the particle outside the box. Suppose we have a box, but we have a barrier. That barrier is of height v0. And we say that the particle can't get over the barrier unless it has energy greater than v0 to do so. But we've also shown that provided the height of this box is not infinite, the wave function outside the box will fall off exponentially. Which means that when we get to here, once again, there is a small but finite wave function psi. And that again means there's a small but finite wave function psi squared. But psi squared is the probability of the particle being at that point, outside the box. And what this is telling us is the remarkable quantum mechanical effect that the particle which is inside the box and which doesn't have enough energy to jump over the barrier can nonetheless go through the barrier and find itself on the outside of the box. And that is the principle of what is called quantum tunneling.